Okay, there we go. So, morning everyone. The couple of housekeeping notes. The complete set of notes for the course, for one version of the course, with all the carbohydrate and amino acid chemistry from previous years, is now available on Blackboard. You can download those. The slides for the previous lectures are up on Blackboard. The announcement went out with the link to all the videos because I was uploading the videos happily to YouTube and then realized that in the syllabus I hadn't actually created a link to the YouTube videos. So an announcement went out yesterday. You can also find it on the course with a link to all the YouTube videos of all previous lectures for the course. So you have lots of resources. Again, as I noted, we're actually going to skip over some of the material that I've taught in previous years. So all the assignments are up from previous years. I'm going to suggest that some of the questions are not going to be necessary because, sorry, I'll be right back. My student locked herself out of her house and by dropping off somebody else, and then thought we had a meeting right now, but I'm lecturing. Sorry about that. Okay. So yeah, everything's up. The full notes are there. We're going to skip over some of that material. I'm going to note which specific questions in the assignments are not necessary. All of assignment 1 is good, but some of the other ones we're going to drop some of the questions because we're just not going to go into that much detail on some of these things to create space for some more of the biomaterial thing. Those of you who want to dig deep into all the minuscule little details of carbohydrate chemistry, it's all up there. Anyways, today, what we're going to discuss is the Koenigs Knorr reaction, what actually goes on in glycosylations, and the considerations that you need to take when you're designing conditions for glycosylation. And in the next class, we're going to skip through what used to take me 4 or 5 lectures. We're going to skip it through one lecture with a few different examples of glycosylation strategies. The full notes are available to you, and you can review those on your own time, but they're pretty straightforward. It's basically the same thing over and over and over again. So it's kind of boring. Okay. So disconnect. When we left off last class, we had just been discussing the Anchimeric effect for about an hour and a half, and we're going to move on and sort of demonstrate kind of this thing in practice and what's some of the details on this and what's actually kind of going on. No, I don't want to switch to the tablet form. If I did, I would have told you. So we're going to start with the what we've covered was the Fischer glycosylation, which was heat the crap out of something in the presence of acid and an alcohol, and you can glycosylate it. That had some major issues, such as heating the crap out of things in acid is generally a bad idea. So there was a real push to find other ways of doing this. So this was the first one available. So you start with brominated sugar. Now, in about a week's time or maybe 2 weeks' time, we're going to discuss protecting groups in carbohydrate chemistry. And for many of you, it might be the first time you're discussing protecting groups. So for now, we're not going to think too hard about how they go on. But what you're just going to do is accept that there are benzyl protecting groups on all of the oxygens. Anyone who's not sure what that is, benzyl is, I was about to use another abbreviation, define abbreviation, which isn't all that helpful. CH2 attached to a phenyl ring. So in a Koenigs Knorr, you take a bromide like this, and you treat this with silver salt, generally silver triflate, and your glycosyl acceptor, which is your nucleophile. I am going to use methanol for now because it's easy to draw. But and then, you know what, I'm actually going to label that another way, but salt, and then solvent. Methanol is not your solvent, it just is your nucleophile. So that's your nucleophile or your glycosyl acceptor. This is your promoter, using the terminology we covered last class. This is your glycosyl donor. So overall, what happens is we glycosylate, which means we do chemistry at the anchimeric center of a sugar. Our major product is going to be an OMe there. Now I'm going to use a short form here. And note what I'm doing here is I'm drawing from the middle of the sugar ring line, like it looks like this, it looks a bit like this C6 group over here, but instead of attaching to this vertex, I'm drawing it from the middle. And that just means every other position is benzylated. And since they didn't indicate any stereochemistry anywhere there, we assume it's glucose. Glucose is the default. So if you see one of these things out of context, it means it's glucose. If you see one of these things in context, like if I had started with galactose or something with some stereochemistry on the left-hand side, and I just drawn that by we didn't change any of that other stuff, it would still be galactose. But if I was doing this out of context and there was no other structures on the page, just this, I would have to indicate, for example, that would be galactose by also drawing in the fact that, hey, it's galactose, look, the stereochemistry is a little weird over here. It's not glucose. Remember, glucose, everything is equatorial. All the other sugars, something isn't equatorial, which is why they're not glucose. But it is glucose in this case. So we get this as the major. And this is the minor. And again, we get the alpha and the beta, and the major product is driven by the Anchimeric effect. So, what this tells us is if we think about this and it's how does this work? If you go back to first year chemistry, first year organic chemistry or second year organic chemistry, whenever you took your first year organic chemistry thing, we can consider that there's two possible mechanisms that could be occurring here. We could have an SN2-like mechanism. So in an SN2-like mechanism, what we would expect to happen is you have the bromine. that bond is elongated already because of the Anchimeric effect, right? The oxygen is donating electrons into the antibonding carbon-bromine bond, as we discussed to freaking exhaustion last class, that elongates the carbon-bromine bond and it weakens the carbon-bromine bond. The Anchimeric effect stabilizes the molecule as a whole. It doesn't necessarily stabilize all the bonds in the molecule. That's a different thing. And you're destabilizing that carbon-bromine bond. It's a very weak carbon-bromine bond. Now you add a silver salt to that. And high school chemistry stuff, you're memorizing precipitation tables and KSP values for things. Silver halides are really insoluble because silver halides make really strong interactions. So silver salt, very, very strong. You could almost draw that. It would be completely legitimate to draw that as a single bond and put the cation directly on bromine. Now, if we hadn't already been weakening that oxygen-carbon bond, we've just really weakened that oxygen-carbon bond a lot. Now, if it's SN2, what would happen is our methanol nucleophile would come in here and would displace the bromine. Typical SN2 reaction. With inversion of configuration, and we would get a beta product. Now, but this isn't major. So this is not an SN2 mechanism for this. Some glycosylations are going to see are SN2, and we're actually going to talk about how you can make this one SN2, but it's not. Because if it was, you would get this. So this cannot be the mechanism, because if this was the mechanism, beta would be your major product. And beta is not your major product, so this cannot be your mechanism. So it's got to be an SN1 mechanism. So in an SN1 mechanism, these are reactions that are independent of the concentration of the nucleophile for their kinetics. And it's because your electrophile just kind of falls apart on itself. And so if we think about that, that's not all that unusual. We just said, stick the silver on that, positively charged. It shouldn't be that unusual in our mind that we would generate the oxocarbenium. Again, remember the term we used last class. So the oxygen comes in, generates this positively charged thing. The leaving group has left on its own. Now our nucleophile. So if you go back to the SN1, we always used to say, hey, the nucleophile's got an equal chance of coming in from the top or the bottom. So any stereochemical information you had in your starting material has been lost in your product. That would be absolutely true if there was not other stereochemical information in this product, but there is. The benzyl group on all the rest of the sugars induce preferred conformations here. There is a preferred top versus bottom. The bottom is preferred for two reasons. One is the Anchimeric effect. Actually, they're both the Anchimeric effect, and we'll discuss why everything comes down to it. I'm trying to think if there's any other way to explain it. It's a complex mixture of sterics and electronics, and we're going to discuss what that is. So that's just the Anchimeric effect. Alpha preferred. And so using this model, we would expect alpha to be preferred, and it is. Okay, so why is alpha preferred? Well, I built some handy models. If you want to try this at home and you have a model kit, you can. If you don't have a model kit and you want to try this at home, I guess you can't, but you probably want, they're useful. See if you can borrow one from somebody if you don't got one. So let's take a look at two molecules, and I'll try and rotate this and make this as same as possible. And I'm going to just pull my video way over here so I can actually see what the hell it looks like to you guys. If there's a way I can make it bigger. No, don't swap my screen with my video. There we go. Okay, so I have a glucose molecule here. So let's just orient ourselves here. This is your ring oxygen here. Try not to rotate it too much. I'll try and keep, man, this is hard to see. Okay, this is your ring oxygen here. This is your C6 carbon or C5 carbon. Sorry, this is your C1 carbon. Even I'm getting confused. And right now I have this as, what I'm going to do is I'm going to turn it into the alpha chair. Okay, oxygen. C1 carbon with a methoxy group on it. C2 carbon with an equatorial OH or OBN. I'm just drawing just one oxygen because the rest of this thing would just bugger it all up. C3 carbon, equatorial oxygen. C4 carbon, equatorial oxygen. C5 carbon where I'm gripping it with an equatorial carbon and an oxygen. Okay, so this is one chair conformation. This is the C4, this is the 4C1 conformation. Carbon 4 is up, carbon 1 is down, as far as we're looking at the plane. So it's the 4-1 conformation. Now, if I switch the chair, ooh, one of my bonds is a little creaky. So I switch the chair to the 1-4 conformation, and now what we can see is that everything was equatorial in the 4-1. Now everything is axial, except for the anchimeric center, which has now gone beta and is now equatorial. Well, it's still alpha, it's just we flipped the chair. This is bad. Everything is axial. This is a bad chair. You do not want to be this chair. You want to be the other chair, where everything is nice and equatorial, and this oxygen, I have to throw that oxygen out. It's wiggly. So everything here is equatorial except for the alpha group, which is fine. But everything else is equatorial. So this is the chair we want. Okay, let's remember that this is the chair we want. I'm going to put it to the side. Now, I have another molecule built. It's the same thing. Even give it the same orientation. Okay, here's the ring oxygen. This is the oxocarbenium this time, though. Here is carbon 1. There's nothing on it. It's that middle structure there. Remember I said I'm going to draw these as boats, but they're not boats. It is better to draw these as half chairs. It's just half chairs make all of us a little bit crazy. But let's say I draw this as a half chair, and I've got two options for the half chair. So this is one half chair I can draw. If I try and sort of represent where things are, this is my, I want to make sure this is right. Just matching, yeah, good. This is matching what you are seeing on the page. So this is the oxygen, double bond to the carbon 1. Carbon 2 is over here. And you can sort of see that there's sort of a pseudo-axial one that's kind of up, and it's sort of pseudo-equatorial when it's down. So if I draw this in here, and it's a whole benzyl group, and I'm going to cheat, we're just going to draw the hydrogens more or less axial. This next carbon behind it is down below the plane of the double bond. I've really accentuated it with my drawing, but it's below. And you notice that the axial position, the one with the hydrogen on it, is axial, and the one with the OH on it is equatorial. It's going back and away into my face right now. So H. Then this one, this carbon-3 is above the plane. Again, the hydrogen is axial. The OBN group is equatorial. And finally, we got carbon-5 over here. Hydrogen's axial, equatorial. That's a good half chair. Everything's equatorial. We like that half chair. Now, just like normal chairs, half chairs can interconvert to the other chair. Now, what should jump at you immediately is that doesn't look great. Like, again, you know, this is clearly kind of axial. These two are kind of bumping into each other. This is not the half chair that we want. There, I had some of the bond angles a little weird. This one's gone axial. This one's gone axial. Everything's gone axial. So again, we've drawn kind of the bad half chair. This is a high energy half chair. So if you're a half chair, you are not going to exist like this. You're going to exist like the other one that we just had to start with, because, oh, that's relaxing. Everything is equatorial. The world is good. Okay, so if you have an oxocarbenium, it exists like this. If you have a chair, it wants to exist like this. Basically, I'll try and superimpose this kind of thing. Like the chair wants everything equatorial, the oxocarbenium wants everything equatorial. That's the way it wants. Now, when we're adding the nucleophile, we go from the oxocarbenium to the chair. So we got two options. So let's say you have a nucleophile coming in. Here's a methanol molecule. It's wiggling around because that's what methanol molecules do. And because of the way that these things work, this is a pi bond, right? And the pi bond is perpendicular to the plane of the sigma bond. So the pi bond is here. It's represented by having these two double things there. Those are going to interact with the nucleophile to form the bond. So the nucleophile comes in axial. Nucleophiles always come in axial on double bonds on rings. They never attack equatorial. They always attack axial. So what happens is I've got two choices. I can either have my nucleophile attack from the bottom, or I can have my nucleophile attack from the top. Okay. If I attack from the bottom, what happens is this guy is going to start being pulled down because it's going to be attracted to this. So as this bond switches from being a double bond and sp2 hybridized to being a single bond and sp3 hybridized, it distorts down. Now, I am playing with a model kit, so it's kind of hard. So as it distorts down, the other guy is going to distort up. Now, my model kit doesn't want to do that. What I hope you can kind of see is that if this goes down, it's kind of in line with this carbon in the back. If this goes up, it's kind of in line with this carbon in the back. That is trying to twist itself into a chair shape. And note the chair shape is twisting itself into is the one I want. It's the one where everything is equatorial. That's a good chair. This is a very favorable interaction. It also happens to lead to the alpha product. So the alpha product results because the most stable twist boat or twist chair, when it reacts alpha, leads to the most stable chair. Now, if it reacts beta, that means it's attacking from the top. And if it's attacking from the top, what that means is this needs to twist up. Now, I'm not able to hold this because now all my bonds are screwed, but it would twist up. So what's going to happen if that twists up? Well, let's take a look at what that looks like on this. So this was our bond. This was the thing that was an oxocarbenium. And this was down. We had the back, carbon was down. Like this carbon here is this carbon here. It's pulled up to make the beta. And you can practice this at home if you need to. But so it's pulled up to make the beta. So that's up, that's down, they're going in different directions. And if I rotate that a little bit, what you can see is we've made a boat conformation. So we've gone from a twist chair to a boat to get the beta to attack from that twist chair. Boats are high energy. So it doesn't want to add it beta, because if it does, it goes to a boat. It doesn't want to be a boat. It wants to be a chair. Well, how do you get the beta then? Well, you can get the beta if instead of reacting from this twist chair, we react from the other twist chair. Because now, beta's from up. What you can see is if the nucleophile is coming in from the top, this is going to be pulled up. And then this is up, that's going to be a chair conformation. But the chair conformation you're going to make, and I'm going to have to rip a bond here to make this work. The chair conformation you're going to make if you attack this beta is the bad chair conformation. Where I ripped the wrong bond. Where everything is axial. So to get the beta, everything you need to go through the twist boat that leads to the everything axial chair, which is difficult to make because it's really high energy. So if we try and sketch this out, so if we have the oxocarbenium, I'm going to call it pro alpha. This is the one that wants to lead to alpha. It's the low energy chair, twist boat. It can go, nothing stopping it going to the high energy twist boat. It's just, it's high energy, which is a reason to stop it. Then this can it has to go through a high energy boat to a high energy chair. Chairs are still better than twist boats, but beta chair, high energy. Whereas this guy needs to go through a lower energy barrier to the alpha chair, low energy. So there's sort of 4 of these things. So these guys, these 2 can switch back and forwards quite readily. I'm going to raise the energy barrier for this. It's going to be higher. No, it's going to be lower than that. It's higher than this, but lower than that. Yeah, I can live with that. So these 2 can switch back and forwards. Those are the twist chairs. They can flip back and forwards to react. But the one that leads to the alpha chair needs to overcome a lower energy barrier to get to the alpha chair, which is also more stable than the one that leads to the beta chair. So alpha tends to form over beta for this reason. Now, this isn't the anchimeric effect that we were talking about, why you're stabilizing the axial group over the equatorial group. That was all about orbital overlaps. And this is kind of a little bit independent of that. But it arises directly from it because the more stable chair has those orbital overlaps already in place because it's the more stable chair. And so it was more readily formed because you had the overlaps in place. Whereas if you create the less stable chair, the overlaps are in place for the beta, but it's a less stable chair, and no one draws glucose. Like, as we said, you can rotate, you can flip chairs, there's nothing wrong with that. And this is beta glucose, where, oh look, you have the right antimeric effect with the stabilizing of this oxygen, but the problem is that everything else is axial, and that's a stupid way to draw glucose. So sure, you have the antimeric effect stabilizing the beta in this conformation. It's just that's not the conformation glucose sits in. It sits in with everything being equatorial because it's not insane. So what we're seeing here with the antimeric effect is that yes, it stabilizes the bonds in the product and lowers the energy of that. But the reason we get more alpha isn't so much because of that. It's because all the transition states and intermediates are leading towards alpha being lower energy all the way along the pathways. So it's more favorable to form alpha than beta. Okay. But I'm lying a little bit. And I'm lying because the alpha stabilizes. So here's what we're going to talk about a little bit here. Antimeric effect. And there are articles now up about this, so you can read about this for next class. It's worth thinking about. And I'm going to post another review. It's a new review. I just need to read it first and ensure that I agree with it. Kinetic or thermodynamic? So first of all, what do those terms mean? What do I mean when I say that a chemical reaction is under kinetic control versus a chemical reaction being under thermodynamic control?
Kinetic means faster, thermodynamic means more stable.
Yes, that is literally what it means. Okay. Faster, more stable. That absolutely correct. Okay. What does faster mean?
Means we reach to the product faster.
Okay, in terms of energies, what
Oh.
does it, so let's say I've got a reaction coordinate diagram. We drew a more complex one yesterday, or just yesterday, 30 seconds ago. Let's draw an easier one.
Less activation energy.
Product. So what would I do to what, and so this is your transition state, right? So this is a very simple one-step process. Starting material goes via transition state to product. Okay. If I wanted to make this reaction kinetically faster, or to favor the kinetics of this reaction, let's say there was another reaction going from starting material to products with more favorable kinetics, how would I change this energy diagram?
In thermodynamic, the intermediate should be in a higher energy, I think.
In thermodynamic, the intermediate should be in higher energy.
Yeah. Because it needs more time.
Maybe, but not
necessarily.
Not necessarily. Thank you. Hazel, do you want to try?
For kinetic product, lower the energy of the intermediate.
Right. Intermediate?
Yeah. So
transition state.
Oh, transition state. Yeah.
So
sorry.
Remember the difference between an intermediate and a transition state. An intermediate is a local minimum on an energy potential. This is a potential energy surface. An intermediate is a local minimum. An intermediate is stable. A transition state is metastable. It is not stable. It is going to fall one way or the other. It is a local maximum. So a transition state is the maximum energy a molecule can have. The intermediate is the minimum energy a molecule can have. So yeah, so we're going to lower the energy of the intermediate. Blue is faster than red. It's faster because on average, more molecules, like if you do this at room temperature, molecules have a certain average energy. More molecules will be able to get over the blue hump than a red hump because the blue hump is lower. It's that simple. Like it really is that simple. There's nothing more to be said about it. Kinetics is lower the hump between starting materials and products. Okay. If I wanted to change the thermodynamics of this reaction, let's say I wanted to make this reaction more thermodynamically favorable, what would I have to do to the reaction coordinate diagram?
To lower the energy of the product.
Or
Of course, wait, what's the word? Raise the energy of the transition state.
perfect. Hazel's perfectly right. So if I wanted to make this more thermodynamically variable, I could raise the energy of the starting material or lower the energy of the product. I don't need to do anything to the transition state.
Just wait, I was wrong. I said the transition state, but yeah.
Okay, I heard starting material, so I'm going to give you marks. So thermodynamics is all about end state. You're comparing the starting material to the product, the relative energies of those two. And what it requires is that the reaction is in equilibrium. So you starting material go to product can go to starting material go to product can go to starting material, and eventually everything just kind of settles in the lowest point. Whereas kinetics, what we're controlling is how many molecules have the energy to get over the hill. It doesn't necessarily need to be favorable. You can have very, very fast endothermic reactions which require the input of energy. The product is less stable than the starting material, but they're very, very fast. If you do that, you're going to need to couple the product formation with something else to make it go one way, normally formation of gas or something. But speed and stability are two different things. So thermodynamics is talking about the relative energies of the starting material in a product. Kinetics are talking about the relative rates of reaction and basically what is the energy of the, which means what is the energy of the transition state. So in the end, rates just come down to energies of transition state. So we can just talk about energies. We don't need to talk about rates because I don't like talking about rates. Okay, so I'm going to draw something that we might want to do, coming back to this, still on the Koenigs Knorr. So we're just using this as a forum for discussion. Same starting material. What I'm going to do now is I'm going to treat this with a different nucleophile. Let's use methyl. Tetramethyl, so that's not absolutely clear. Nitrogen, 4 methyl groups around it, Br minus, whatever, dichloromethane is solvent. 0 degrees Celsius. My nucleophile is bromine, my leaving group is bromine. All this talk about alphas gets me excited, except we go to the beta bromide. This is in equilibrium, but it favors the beta. We've just been talking all this time about the anchimeric effect favoring the alpha. If we go back to that original slide where I started showing the relative percentages of alpha and beta in everything, I was saying, hey, look, in general, with just the OH, with just the sugars, if you want to look back through your notes, the beta still predominates. It just predominates a whole lot less than you would expect. And that difference was the anchimeric effect. And then when we had a reaction and we stuck in a methoxy group, the alpha predominated. So the anomeric effect favoring alpha. Do you think that's primarily a kinetic or a thermodynamic effect?
Oh, maybe.
I don't know if there was an answer there, Ronaz. I just heard.
Alpha is the kinetic.
Yeah,
And beta is thermodynamic.
right. So the anomeric effect favors kinetics. And remember, I was just talking about the half chair. We were playing around with the molecule and talking about all that. All that was about energies of transition states. At no point did I talk about the energy of the product. I talked about, oh, look, this chair is unstable, but chairs can flip. I was talking always about energies of transition states between the starting material and the product. And what we saw was that the alpha was favored because the energy of the transition states was always lower. The energy of the intermediates that go with those transition states were also lower because intermediates track transition states. But the beta is normally the thermodynamic product. And it's because sterics are still sterics. So although the anomeric, and so the thing to remember is although the anomeric effect really helps stabilize the alpha thing, it gets really easy to think, yeah, alpha anomeric effect stabilizing, because it's like 3 words and they connect together and it's just easy to get in there. Sterics are still really, really important, and sterics favor beta. Sterics always favor beta because you don't have 1,3 diaxial interactions. Like no matter what you do, this bromine is bumping into these hydrogens. It just is. There's no way around it. That is it's called a 1,3 diaxial because carbon 1, carbon 2, carbon 3, if we're counting the sugars, but you can, the 1,3 doesn't care about which direction you go. The 1,3 don't mean sugar 1 and 3. Diaxial because those are both axial. Interaction because they are interacting. They do not want to be interacting. Whereas here, the bromine is now equatorial and a hydrogen is now axial, and you don't get smaller than hydrogen. Hydrogen's the smallest thing you can have. And so now hydrogens are having these 1,3 diaxial interactions. There's nothing we can do about that, but at least we have the smallest one possible. There's no possible smaller one, whereas bromine is a pretty big atom. As things get bigger than bromine, like methyl groups and stuff, the effect gets even bigger. And we saw that equatorials are favored for steric reasons with the reverse anomeric effect. And there it was so dominant that we really, no matter how positively charged that thing was, no matter how great the anomeric effect was, it's just basically entirely equatorial because it's just so freaking huge. So I'm going to say primarily kinetic because there are thermodynamic aspects to this too. Because remember, what we're talking about is when we're discussing kinetics versus thermodynamics, we're discussing energy descriptions of the potential energy surface. And everything kind of interacts with everything else. You can't fully separate the two. And the anomeric effect is one of the messiest interactions of that. More thorough descriptions in reviews I sent, and a more thorough description in the notes I also made available, which I'm not going to go through as much detail this year, if you're really interested. One of the questions on the assignment, and one of the questions I do like asking on midterms and finals, is discuss the anomeric effect and the kinetic versus thermodynamic nature of the anomeric effect. Mostly because I really like stereoelectronics. There are wrong answers, but there are multiple right answers, mostly because we can't actually agree. And I don't expect you to write a 40-page essay on it. but just touch on some points to show that you have an understanding of the concept. And you need to understand the concept because it drives everything that goes on with sugar chemistry. Okay. So I want to talk about what's going on with this bromine reaction, just really stepwise, really stepwise, what is going on with this bromine reaction. And I have my notes here somewhere, and I minimized them, which wasn't wise. Why did I minimize my notes? Sorry, just take me a second. I'm just a moron. So let's talk about this this whole bromine thing that we just saw. So we start with an alpha bromide. Now in this reaction conditions we had tetramethyl ammonium bromide solvent, there is no promoter. We don't have anything activating this. We're just letting it go. So nothing's binding to it. And when we were discussing, it's possible this can come in SN2, but SN2 is not very common in sugar chemistry, and it's difficult to displace a leaving group with the same thing, SN2 style. It just doesn't tend to actually get to the transition state. They're normally very high. You normally need to activate the leaving group, and that's not happening. So we are going to do SN1. Now, I'm going to just draw this over here. It is tempting, and I will accept it. And we've been drawing it this way, and I'll accept it actually in exams and things when relevant, and we're not trying to discuss these minor details, to simply draw, lone pair comes in, kicks out bromine. Basically, the anchimeric effect taken to an extreme, where instead of sharing some of the electron density with that antibonding orbital, we just dump it all in, and we break the bond. But that's not accurate, because that will make a double bond, and you can't make a double bond from a chair. So the first thing that needs to happen is this thing needs to flip to a boat. If it doesn't flip to a boat, it doesn't go. So once we flip to a boat, click too many buttons. What can happen now is we can have what we just drew. I'm going to erase it so it's not in the permanent notes because it doesn't do that. Then we have made our oxocarbenium ion. But our bromine atom is still lying very close. Again, there was nothing taking it away. There's no promoter. It's a Br minus sitting really close to an oxocarbenium, and it's set to do the favorable chair that we want, the low energy chair, to go back to starting material. So the most likely thing to happen is we're going to go back to starting material. So in all cases, I've drawn these equilibrium arrows as equal, but if we're actually just taking them step by step, they all favor going backwards. Because in every case, the structure before is more stable than the structure after. Chairs are better than boats. Boats are better than charged species. Okay. Now, what can happen here is this is more or less equal. the Br minus kind of flips around and starts sitting more on the top face of this boat or half chair. Now remember, the attacks are always axial for these things. So the only way this boat or half chair is a half chair, and I'm drawing it as a boat because I said because half chairs are boring to draw. The only way this half chair or boat can react is alpha, because the attack has to be axial. And if it's axial, it has to go back. But now the bromine has wandered off and it's no longer sitting alpha. So some of the time, this can now flip to the wrong boat. Now again, what in this boat conformation, a lot of our equatorials have gone axial. This is not a good boat. We don't want to be in this half chair or boat. It's an unstable one. I will try really hard to keep my N's and R's looking different. But our bromine is still on the top face now. But now that we've flipped this thing, now the axial attack is going to be from the top. That's going to give us the beta product. And so that's what can happen. Why is this favorable suddenly? Why am I drawing this going towards the product? Well, because anything charged is always worse than anything not charged. Like conformations are bad and everything, and it's awkward and all axial. But not being charged is the best thing ever. And then this can relax. To the all equatorial boat. I suggest you draw in the substituents and play with the model kit and look at the half chairs on these kinds of things. But this is what's going on here. The bromine has gone from being attached to one chair to being attached to another chair. And it's done that by chair converting to boat, boat kicking out nucleophile, nucleophile rearranging to the new face and just moving, boat flipping to other boat, nucleophile attacking boat to create chair. You know what, I skipped a step. I will put this into, it should actually have gone through a boat intermediate. It still is all axial there. All axial here. All equatorial up there. Oxocarbenium going to the boat, boat going to the chair, the wrong chair, because that's the way it unfolds, chair going to right chair. So we have this sequence of events that occur. Now, all of these are unfavorable, except this is all a pathway between two extremes. And when it comes down to it, we can simplify this whole thing by saying alpha, beta, all the other stuff. I put it into a single mound. Of course, it's not a single mound. I can draw individual peaks and valleys in between each of these. Each of these is an intermediate. There's a transition state between everything I've drawn here. So this mound, I've drawn a single bump, but I really should have 1, 2, 3, 4, 5, 6, 7 bumps. But I'm just going to say, hey, it's all happening in one. And what I really want to highlight here is the beta is more stable than the alpha. This is thermodynamically favorable, even though kinetically each of these steps is unfavorable. And thermodynamically, if I'm just considering any of these intermediates relative to the starting material, it's unfavorable. One of the worst places is actually right before I convert to my final relaxed conformation. But it's favorable overall because the final product is more stable than the starting material. And, you know, chemistry always finds a way to get to the most stable place it can. Okay. Any questions about this? Cool. Okay. So, I could basically spend the entire course talking about this, but I'm not going to. I think we're happily done. What I want to talk about is what we can do with the Koenigs Knorr to play with it a bit. So, if we started with the alpha bromide, and we use the conditions that we drew first: silver triflate, dichloromethane, and then methanol as a nucleophile. I said we went to the alpha product. Why is that? Because you're going to go to the oxocarbenium, you're going to make the most stable half chair, the methanol is going to attack. And once the methanol attacks, the reaction is irreversible. So the final step of making this carbon-oxygen bond is irreversible. Whereas in the case I just showed you of all the bromine stuff, none of those steps are irreversible. Everything can go back and forwards. Whereas here, the alpha is irreversible. So although the beta methoxy is more stable, it never gets a chance to form because the alpha forms first and it's an irreversible step. And now if I start with the beta bromide, which I could just make using the conditions I just showed you, and I treat it with the same conditions, what's my product? So if you need to scroll back and take a look at the mechanism of how this silver thing worked. What do I expect? Do I expect the alpha or the beta methoxide?
Does it happen?
It happens. This is actually a very, very fast reaction.
Oh.
It's actually much more reactive beta than alpha. But good. Always a good question. Looking for the trick.
Because it couldn't turn into beta in the first reaction, so I thought maybe it's
Well,
not
here
able
we
to
just
happen.
showed how we can make the beta bromide from the alpha bromide. So let's say we have the beta bromide and we use these same conditions. What the beta will have to do is it will have to flip to that unfavorable boat and then interact with the silver and make the oxocarbenium. So if we think about these interconversions, where we were talking about back here, and we were saying, hey, so if we start with, we start with the beta chair of the bromide, we add the electrophile or the promoter. So it takes us to the oxocarbenium that's pro-beta. That can interconvert with the oxocarbenium that's pro-alpha because the half chairs can flip. So will the beta starting material give me a beta product or an alpha product under those conditions?
Still alpha.
Still alpha. Once you make the oxocarbenium, both go through oxocarbenium, right? So this one's going through this one. This one goes through this one initially. But these interconvert. And it favors the top one because in that top one, everything was equatorial, so it's a much more stable oxocarbenium. The bottom one, everything is axial, it's a much less stable oxocarbenium. So although the beta starts with a different oxocarbenium that it's formed because it's beta and it needs to form the other boat, it switches to the other one. The oxocarbeniums convert really, really fast. And then it reacts kinetically to give us the alpha product. So it doesn't matter if you go through, so this is maybe a key takeaway. If you go, that looks like you go through an oxocarbenium, initial stereochemistry at Anchimeric center is irrelevant. It doesn't matter. You lose all that information. It gets deleted because the two oxocarbeniums can interconvert really quickly. This is exactly like what we think with an SN1 reaction. You lose the stereochemical information. And I said these aren't, and then normally what we say is, okay, in an SN1, you lose stereochemical information and it's a 50-50 shot. Here, you lose the stereochemical information. It is not a 50-50 shot because there's all these other groups on there that are inducing one conformation over the other. But you've lost the data and the memory of what was there. And so you favor the kinetic product in these cases, which is always going to be the alpha. Okay. What if I don't want the alpha? I want the beta. So what I'm saying here is that using a traditional Koenigs Knorr, you're fucked. You can't get the beta. You will get the alpha. It doesn't matter if you start with the alpha or the beta. If you use these conditions, you will get the alpha. It's kind of nice to know. But what if you don't want the alpha? Well, there's two ways around this. So one is specific to the Koenigs Knorr. This doesn't work great. It's okay. On paper, we're going to say it works amazing. In practice, it's kind of a mess. So in this case, if you use a silver solid surface, I'm going to give you some information, and then we're going to discuss mechanism. Ditto, so same conditions. Okay, so take the alpha bromide, treat it with these conditions, silver salt, like solid silver, like, you know, teapot, take your teapot, stick in your reaction flask with some methanol, and boom, you get your product, and your teapot will be probably destroyed, covered in bromine, just be a mess. So don't take your teapot and do this. unless you really want a new one and you hate your family heirlooms. So the second one, if you take the beta and you do the same conditions, you get the alpha product. So is this likely to be going through an oxocarbenium based on this information? Remember this statement. If you go through an oxocarbenium, initial stereochemical information at the antimeric center is irrelevant. Is the stereochemical information at the antimeric center irrelevant for the outcome of the reaction under these conditions? Well, it's not, because we got different products. And the only difference between the only difference in the entire thing is the stereochemical information at the antimeric center. One is equatorial, one's axial, top one's alpha, bottom one's beta, and we get two different products from those. So the stereochemical information is not irrelevant because it's the only difference and we get different products. So these are not going through oxocarbeniums, because if they were, we would scramble that information, we'd lose it, and we would get the same product. So what's happening here is, in a previous example with the silver salt, we formed like basically a bromine silver covalent bond. And that was because you had silver plus floating around desperately looking for electrons. Now you got silver solid. It's fine. It's got all of its electrons. It's happy silver. So we've got like a mound of silver, silver bound to silver, bound to silver. I'm not an inorganic chemist. I have no idea what this actually looks like. But you know, there's silver stuff. And on the surface, it's silver, like not silver oxide, it's silver. So, you know, your sugar comes close, the bromine goes, ooh, I like silver a lot. So the bromine just like donates electrons to silver because it loves silver so much. If the bromine is donating electrons to silver, it's becoming slightly positive. It doesn't want to be positive, so what does it do? It sucks more electrons down from the carbon, which elongates the carbon-bromine bond. Because now the bromine is pulling more of the electrons in that carbon-bromine bond towards it. It's partially breaking that bond. Of course, now what's happening is the oxygen is perfectly happy to help bromine break that bond, because that's what it's doing with the antimeric effect, is it's doing electron density to the antibonding carbon-bromine bond. So we're really elongating that carbon-bromine bond. The bromine's really happy to be giving its electrons to silver, but it hasn't completely committed. We haven't broken the bond, we've just elongated the bond and weakened the bond. So now if your methanol coming in, going, ooh, that's a nice big juicy delta positive on that carbon. I like the look of it. I'm a nucleophile. There's an electrophilic carbon because bromine is pulling all the electrons away because it wants to give them to silver instead of share them with carbon. And so let us do an SN2. And that's what happens. The silver isn't enough to break the bond now. The silver metal was, or the silver ion was, the silver plus, the silver triflate, great. That's why we use silver triflate, because triflate completely dissociates. It's the, I think we talked about in the first class what triflate was. It's the best leaving group that there is. It's just the best. So that was silver plus. This is not silver plus. This is just silver. And it likes bromine, but doesn't like bromine that much. So methanol is going to come in here and help break up this happy carbon-bromine marriage. Whereas in the previous example, bromine just left. It didn't need help from the nucleophile with the silver triflate. Here it does. So you get the same thing if I draw the beta bromine coming in. I'll just flip the sugar around, but it's the same idea. You get an SN2 like. Okay, so this is one way we can make betas. It's not the best way. The best way we can make betas is something called Anchimeric assistance. In my notes, I always write as Anchimeric assistance because that's what I was taught, and that's wrong. It's Anchimeric assistance. It's just I have been doing it wrong for 20 years. Because somebody corrected me on a paper we published saying, Dr. Trent, you don't mean Anchimeric. That's not a thing. You mean Anchimeric. And then I got like really upset and I said, no, of course I do. You're a moron. It's Anchimeric. And then I looked it up on Google, and the only examples of anyone using the term Anchimeric are my own work. So I'm wrong. The word is Anchimeric. Anyways, Anchimeric assistance. What the hell is that? So I've been really careful that we've drawn benzyl protecting groups on all of this. Now, what if we do something a little bit different? Okay, so we're going to have bromine. And now I'm going to put acetate groups. So if you don't remember, that thing at the top there is an acetate group. And I've just abbreviated as AC because 3 lines is less drying than 5 lines. The AC takes up a little bit less space, but that's what it means. Where that's the bond, where the bond is formed. So it's a carbonyl with a carbon. So if I take this and I use silver triflate, methanol, dichloromethane, same conditions we've been using the whole way along. When we had the benzyl protecting groups there, for everything we've now been discussing for the last hour and 20 minutes, you get the alpha product. You know, half oxocarbenium, half chair, preferred half chair, not the other chair because the other one is high energy, so we're going to go with the low energy one, blah, 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 alpha product. It's not what we get here. We get the beta product. And we get the beta product not as preferred, we get the beta product as the only thing formed. In all the other cases, the alpha product was preferred. I always wrote major, I hope. And it's fine if you draw it as the alpha product coming through those conditions, that's fine. Major product, all you need to draw. We'll pretend that minor products are not a problem and that columns are a problem for somebody else. As Hazel and Ronaz know, that's not the case. In here, you only get the beta. You will not find any alpha. I shouldn't say none because there's a lot of molecules in a mole, but very, very little. Negligible amounts. So, something different's happening here. Again, I'm going to use that comment. I didn't change anything at the reactive center. I changed stuff next to it, but I didn't change anything at the reactive center. So what's happening here is no change in mechanism. The mechanism is identical. Silver comes in. Bromine uses a lone pair to attack silver. Thing ring flips to the boat because it has to. So far, absolutely identical to what we drew. Oxygen lone pair comes in, kicks out bromine. Make your oxocarbenium. Identical, nothing different. This is where it gets different. Because oxocarbeniums aren't great things. And so the oxocarbenium now is sitting in that half chair waiting around for a nucleophile to come in to react with it to give you the alpha product. But the nucleophile needs to find this. Like, imagine you're, like, take a look around the room you're in. Imagine somebody else is in a room with you. And My phone's ringing, so I'm just gonna turn down my ringer. Imagine somebody else is in a room with you, and you're both blindfolded and you need to find each other. It's gonna take some time. And if your room gets bigger, it's gonna take more time because there's more space for the two of you to move around. Now, instead, imagine that you're in that room and you use your hand and you try and slap yourself on the forehead. It doesn't matter how big the room is. It doesn't matter how many other people are in a room. You're going to be able to slap yourself on the forehead at the same rate, no matter how many other people. This is actually starting to hurt. How many other people are in the room, because the pen is kind of hard, or how big the room is. It's independent of reaction of concentration. It's independent of relative concentration of two species, because this is an intramolecular reaction. So the molecule is going to slap itself on the head, and the oxygen of the acetate group at C2 is going to react with the sugar. What does that do? Well, it gets us this species. Okay, I don't see how that's any better than the oxocarbenium off the top. The oxocarbenium had a positive charge on oxygen with double bond to carbon. Here we have a positive charge on oxygen with double bond to carbon. But it is better. Why is it better? Why is this species so much more stable than the traditional oxocarbenium? The rest of the acetates are just hanging out. They're not part of the answer.
Because the other oxygen kind of resonate with it.
Absolutely. Except I'd remove the kinda. The other oxygen resonates with it. You're just right. Because you got a resonance structure. And nature loves resonance structures, because you are delocalizing that positive charge onto two different oxygens. So if this thing's hanging around, yeah, sure, this is all in equilibrium, but we've just massively stabilized that oxocarbenium because we were able to move it onto two different oxygens instead of one oxygen. That's great. So unsurprisingly, when there's an acetate at C2, you don't have the oxocarbenium sitting around, you have these guys sitting around. Now, the acetate group is a great leaving group. It's a positively charged acetate group. This is an amazing leaving group. So as soon as anything like methanol comes around, it goes, yep, this is an amazing SN2 reaction. Like, this is like a triflate or an iodide on steroids. This is a much better leaving group than anything else. And it can't attack alpha because the freaking acetate is there. And this guy can't attack beta because it can't reach. You can't have a trans, well, it's harder to make a trans 5-membered ring. It's very easy to make a cis 5-membered ring. It's fast. So the acetate goes cis. The acetate is axial at the anchimeric position, equatorial at C2, which then allows the methanol to come in. If we want to push from this resonance structure, we can, which then gives us, well, actually this goes us straight over to the product over there. So this is anchimeric assistance. I'm still going to pronounce it anchimeric assistance, even though I'm wrong, because it's just, I will forget. But try not to get into this habit. So the chemistry is the same, oxocarbenium is the same. The problem is now we have what's called a participating group at C2. It is called a participating group because it participates. kind of like Ronaz and Hazel, who are participating students in this class. So, and who are really chalking up their participation marks. So we have the participating group participating in the chemistry, and we can call, so we'd also call, I might refer to it as an Anchimeric assistance group. This overall effect is called Anchimeric assistance, and it relies on having a C2 participating group that takes the oxocarbenium, stabilizes it, and blocks the alpha phase, forcing beta attack. So in general, to sum up today, get alpha by relying on an Anchimeric effect. Kinetic product. Get beta through witchcraft, like using solid silver. You're kind of cheating. So I'm going to say through cheating / avoiding oxocarbenium, or Anchimeric assistance. From oxocarbenium. I really wish to say that there was a lot more going on in sugar chemistry than that, but that's really what it comes down to. We're going to walk through a few different ways we can make oxocarbeniums with different things, because there's problems with the bromide. It's not a great group. But really, we're either going to find new ways to make oxocarbeniums with things that are more stable or less stable, or more reactive or less reactive, or can play with this or play with that, or play nicely with each other. But really, we're just kind of fiddling around the edges. It's all oxocarbeniums. Or we try and avoid the oxocarbenium altogether. There's a few other ways to do that. Or we use Anchimeric assistance to get the betas. That's it. Like that's really all there is to it. Yeah, big secret of carbohydrate chemistry. Okay, so I'm going to wrap up there today. So we're at 9:53. So next class, we're going to be discussing a few different glycosylation techniques, glycosyl sulfoxides and sulfides, and glycals. I'm going to skip everything else. So there's notes on glycosyl fluorides. We're not going to talk about them because they don't really matter. And there's notes on trichloro. We'll talk about trichloroacidimidates because they're cool. But we're going to drop everything that's not trichloroacidimidate, a glycosyl sulfur thingy, and a glycal. And we'll talk about what those things are next class because we haven't discussed that yet. But if you want, you can take a look through the notes in advance. Lectures from previous years are also available on my YouTube channel if you really, really want to watch those. And if you're lost from this one, I do describe it differently every year on the basis that maybe a different way of describing it works. You can also take a look at some of these concepts on Wikipedia. I've also uploaded a couple of articles under literature. There is one couple on the Anchimeric effect, and there's one which is just really interesting reading about Fisher's determination of the structure of glucose. It's a great logical puzzle. I love it so much. I'm not teaching it this year. I won't be quizzing on it. But if you like logic, and you're all scientists, so I assume you like logic, it's a mind-blowing proof. And proofs are always mathematical, so it's really cool to see a chemical proof. Anyways, that's it for today. I will see you guys on Monday. Have a really good weekend. How do I stop recording?
Thank you.